First of all, thank to Pino, thank to everyone to be here. Thank to Pino for inviting me here. As Pino just said, it's I suppose it's a very informal way of informal talk. So feel free to ask any question anytime. So this is a work which has been done in joint collaboration with quite a few people, and I have to acknowledge the fact that the workforce behind here, the driving force behind this is Federico Cati, which at the moment is in Luxembourg, and many other people around the world. And it's based basically on two main publications. One is currently under review. Doesn't go on. Okay, got it. So there are two parts in this talk. The first one is it will be dealing with exotic properties related with non-Hermitianity of some given system. I'll discuss in a bit. And later on, the main focus will be on light matter interaction with some topological information in it. And on the topic would be on, again, a topology which is related with Hermitian and non-Hermitian things. So I'll be, of course, more details in a little while. But as a motivation and also to set the setting, I will basically describe the main situation that I will consider is Waveguide QED. And as you may know, what is Waveguide QED? Essentially QED in Waveguide. So you have emitters, and you want to see the properties of lights emitted by these two-level system, emitters or whatever, in an interesting environment, which is usually, we will think about them as 1D systems, so waveguide, or even 2D systems, for example. So it's a peculiar type of environment in which these objects emits light. And they can be structured, so interesting structure, band structures. And due to this underlying structure, we can see that the emitters behave in a very peculiar way. So that's the idea. So what type of systems nowadays can be realized in which you can actually perform this type of exercises? So you can have emitters, which are superconducting qubits. You can have silicon vacancies, quantum dots, cold atoms, and this can interact with waveguide, which are actually made within the same superconducting devices. Or you can also have cold atoms, for example, which interacts with nanofiber, which essentially are fibers which are stretched to the point in which they are so thin that the evanescent waves of these waveguides can freely interact with atoms which are placed on top of them. So this is the type of physics that I will look at, and in particular, there's also a peculiar type of object that sometimes are kind of very fashionable these days, which are these so-called giant atoms, in which you have these emitters which no longer interacts only in one point to their environment, to the two-level system or whatever it is, to the waveguide, but they can interact in multiple points at the same time. So as if they have one point here in which they interact, another point here, maybe another one. So this can give rise to interesting new physics, which is being explored in the last 5 years, not only recently. So the goes on here, but not there. What? Oh, okay, here. Okay, so a little bit of lag. So the cartoon picture, what I will discuss is just a collection of two-level emitters, and this collection of two-level emitters will interact with a waveguide, which can host a continuum of modes, and but it's sometimes easier to picture these continuums of modes rather as a collection of cavities, or discretized cavities. So you discretize them, and then of course you can take the continuous limit. But the fact that these are discretized gives, so as I was saying, these two-level atoms coupled with the structured waveguide, and the fact that you have this structured waveguide can give rise to interesting, again, band structures in in this environment, this waveguide. Of course, we will deal with at the quantum level, and the way to describe this is a standard way. So we have bosonic modes and two-level atoms. That's the idea. So the approximation that I will do for this story will be a weak coupling approximation. So we will assume to have atoms, these emitters, which are tuned in such a way that they are kind of detuned from possible photonic bands of your waveguide. So these are the bands, the eigenenergies of your photonic band, of photonic structure environment, and these are detuned. And we assume that the interaction is weak enough that the weak approximation is valid, so rotating wave approximation is valid, and these type of things. Within this approximation, you can go to the second order approximation, and by using some resolvent techniques, which is very easy in this context, you end up with an effective Hamiltonian, which describes the way in which emitters interact with each other. So in this approximation, the atoms are effectively, at first order, decoupled from the waveguide. They're only coupled to each other to second order interaction, and this is the way the interaction is described. So that's the most of the interesting things that we will discuss today is contained in this expression, where this is the Hamiltonian of the photonic bands, and this is the frequency of the emitters, and that's the coupling energy. So that's very simple. So now the waveguide has a continuum mode. Generally, if you have translation invariance in waveguide, but you may observe that when you place an atom interacting in that way with your waveguide, you may, not necessarily, but you may observe the appearance of atom-photon bound states. So photons which are emitted by these emitters generally tends to go away somewhere else. But in some peculiar situation, you can observe the presence of some dress states, so-called dress states, or bound states like this, in which the photon somewhat remains confined in the neighborhood of the atom. So it's kind of go back and forward from the atom to this neighborhood, and somehow form this bound state, which is a linear combination of the atom being excited and the neighborhood of the atom, and a photon remaining in the neighborhood of the atom. So this is the excitation of the atom, and this is the photon in the neighborhood of the atom, which can be calculated again using technically the resolvent technique, and this is the resolvent of the Baer lattice. But never mind, this is not the point. Is the resolvent, is the green function. No, that G. G is the coupling. Is the coupling energy.
But not second.
Yeah, it's this same the energy which the atoms is.
No, sorry, X is an atomic state.
X describes the position. It describes how is the atom. Or X is the position in which the atom is coupled.
Okay. Okay. Yes.
Okay. And this whole thing describes the spatial distribution of these bound states, the photonic part of the bound state. But this is not the only thing that you can gain from this expression, because nicely enough, if you want to have an intuition of how these effective Hamiltonians is done, you can interpret in terms of the shape of this bound state, because the way in which these atoms interact with this one is the strength of the interaction between them is actually given by the amplitude of this bound state as seen by the position of the second atom, in the position of the second atom. Okay.
I didn't understand. This Hamiltonian describes the coupling between two atoms.
Yes.
But where are the operators of the atoms in this effective Hamiltonian?
These are the operators of the atoms. No,
Yes.
these are just say that in this case these are just a two-level, it's a 2 by 2 Hamiltonian. This one.
But there is the Hamiltonian of the photonic buff, which is the inverse of, we have to do the inverse of the Hamiltonian of the photonic buff.
Mm-hmm. And this would be again is the projected here. You should project this in the degrees of freedom of the two sides of the photonic band. Okay. In order to have the effective Hamiltonian between these two, you have to project this quantity on the two sides.
If I understood correctly, probably he meant where the sigma of the ith atoms in that formula, like
okay.
Omega E is coupled to the excited state of the atom.
The operator. They are disappeared. They already. These are already an effective description of the atomic degrees of freedom. So this is. You doesn't appear explicitly.
Okay, then.
Okay, this is just an identity.
Yes.
Okay. Understood.
Okay, so these are matrix and these are not matrix.
So if you project this Hamiltonian
into the subspace of the position of this and this one, you get the effective Hamiltonian between these two.
And this is like, and the qubits become a network or are near neighbors complex?
If you have only these two, is a near neighbor.
But in general,
Can be as complicated as you.
So HPS, the full Hamiltonian, H effective lives in the
HPS, the full Hamiltonian of the band.
In the same Hilbert space of HP, of course, and it's only approximated the second order.
Yeah, kind of. Yes.
This is the approximation of the rotating wave part.
Yeah, below this, there's a weak coupling approximation.
Is the dispersive?
Yeah.
Is a dispersive Hamiltonian, essentially. Yes. You could do also non-perturbatively, but there is a little bit. There's the rotating wave approximation is still. I will always assume anyway.
No, the point is that if you put omega E in the bands, then you have to suffer a bit more.
What's omega E? Okay. You can still do it. Actually, it's perfectly done. You still have to apply a weak coupling according to Southern. Exactly. You obtain a non-emission Hamiltonian.
Yes. No, I'm interested if you have a discrete, if the band is not continuous, but we.
No, even if okay. No, you can do it also if it's this. Okay. So of course you can do the converse. Vice versa. Of course you can calculate the bound state of this and calculate the effective Hamiltonian looking at the bound states of this in this place. Okay. So that's and because everything is emission here, what you get is that the effective Hamiltonian becomes emission as well. So that's, in a sense, is interesting. And from my point of view, from a motivational point of view, is kind of boring because you can do many things with this type of emission lattice with emitters coupled to it. You can also show very nicely, you can show that if you have a structured environment, a structured photonic lattice, you can devise interesting atom-atom interactions which inherit some nice properties of topological properties of the lattice, and you can exploit this in many different ways. But this is not the topic of today. You can also show that if you place an atom in a peculiar 2D lattice called the Haldane lattice, you can observe that the formation of peculiar bound states where the photons kind of orbits around the atom in the center. So there is one photon orbiting around it. So it's and this photon is again has interesting topological properties. So again, playing this game, you can also show that if you have your photonic lattice, which has interesting properties such as the SSH model, which I'll discuss later on what it is, you can have shape of the bound states which are typically chiral, in the sense they are asymmetric. And these are in the community of people that want to devise effective Hamiltonian. It's kind of a nice thing, this chirality, because you want often, in many situations, try to devise Hamiltonian which are chiral, in the sense that the interaction goes only in one direction rather than going both directions. And for many technical reasons, for many also applications, it could be very useful. The problem is that even though the shape is chiral here, you can show that no matter what, because you are in an emission configuration, the effective Hamiltonian is reciprocal. Again, because of we said before, you have an emission Hamiltonian, you get an effective emission Hamiltonian. So and emission Hamiltonians are always reciprocal. We want to go beyond that. So we want to see what happens. See if you have an environment, bath, which is not emission, and see what you can gain with this in this game. So the idea now is done in collaboration with these people here. Sorry, I want to give credit to the people. So this is the Federico that was mentioning before, and of course the other people, which, well, just to say a few words, what are non-Hermitian, how to think of non-Hermitianity in this context. Non-Hermitianity, as you know, guarantees you the fact that you have real eigenvalues, Hermitianity, orthogonal complete eigenbasis, and so forth. The problem is that when you have non-Hermitianity, you have to give up real energies, you have to give up orthogonality between eigenstates, and you may think of these not Hermitianity and not real eigenvalues as having an imaginary part of your spectrum, which can be interpreted as a lifetime of your eigenstates, right, as standard things. So a standard toy model, that just to picture what is going on in this type of situation, is when you have a two-level system in which you have an interaction between the two levels, and you have a possibility of losing excitations or gaining some excitations. And this peculiar simple model is already complicated enough to see some interesting physics happening. So you have a loss on the lower level and a gain in the upper level, which are on the same amount. If you do that, it has this symmetries, guarantees that something interesting happens. And if you look at the spectrum of this very simple Hamiltonian, you see that as you change the value of gamma j, gamma and g, you can see that the part of the spectrum in which the eigenvalues are real, and part of the spectrum in which the eigenvalues are just differ by the imaginary part. In between, there is one sweet spot in which the eigenvalue coalesce, go to the same value, which seems kind of boring from the Hermitian point of view, but here happens something that in Hermitian physics cannot happen. And it is the fact that actually the eigenvectors, as you move in this direction, becomes less and less orthogonal, and as you get here, they actually coalesce. And the two eigenvectors becomes the same, and you lose actually one eigenvector. It means that your Hamiltonian becomes defective. It's not anymore, the spectrum is not anymore complete, your Hamiltonian. So wait.
About this thing. So you're saying that when you have real eigenvalues here,
you have, yes.
You can have two orthogonal eigenvectors.
Exactly. Two not overlapping eigenvectors.
Yeah, two distinct.
Okay.
Two distinct eigenvectors.
The imaginary. When you have complex eigenvalues in general.
Yeah, in general, if you have two distinct complex eigenvectors, you have two eigenvectors, you can distinguish them.
The space, the dual space, and you need.
Exactly. As you get close here, you may think that just the two eigenvalues just is the same, which happens many times.
It's degeneracy there.
Yeah, you can make, exactly, there is a degeneracy at this point. And you can think of this degeneracy as a standard degeneracy that you see in Hermitian method. But it's not a standard degeneracy. It's actually the fact that the two eigenvectors, you cannot, exactly. So the spectrum, the Hilbert space, the number of eigenstates of your system is 1 instead of 2.
Yeah.
Okay, so you have a defective.
And also, I have another question. That if you have this non-Hermitian Hamiltonian, then you make the Hermitian conjugate, you get the antichiral. I mean, you are changing the direction of the.
So if you
take your H and you do
of course,
H down.
the time reversal version of this. So you take the complex conjugate of this is the reverse process, of course. Yes, indeed, yes. So this naturally breaks time symmetry in this type of situation.
There's a comment. You have exactly the same thing. If the gamma, instead of going out, they are
exactly
one of
exactly.
the other. But you cannot, of course, write the emitter. You can do lambda. And it was this game I told you on zero effect.
Oh, okay. Now, the idea is to translate this idea into a waveguide. So now, how do you structure the non-Hermitianity in a waveguide? You place a losses, right? So the idea is have a waveguide, these are normal, have a waveguide which is lossy, but do it in an interesting way. So structure purposely your losses in a non-trivial way. So maybe you don't put the same losses everywhere, but you put it in a again, structure the way and see if interesting physics can come out of this. So here is an example, which is not very kind of the minimal. Unfortunately, this is minimal. Doesn't look like, but it's a minimal example. So these are an Hermitian lattice, which is called Lie photonic lattice. Very, very complicated, but you focus only on two type of cavities. These are two cavities, cavities A and cavities B. Now let's put some non-Hermitianity in the game, just placing some losses, but only on level B, on cavity B. Okay, so this already put some structure in your losses. So this is a passive system. What this means passive? There's no gain, so you only lose.
The direction is up.
No, the direction is just any. No, it's not suggestive of anything. It's just
saying that it's only. I mean, the expression are only going away.
It's just going away in that sense. Yes. There is one exceptional point in this lattice, and is given by gamma equals to 2j. J is interaction expressed here. Gamma is the loss rate. Now there's you see there's no explicit directionality, so it's perfectly symmetric if you go right and left. And this is lossy. Passive means that it can be done easily in cavity QED, this type of situation. So the problem is cavity QED usually is pumping. So it's very hard to do it in a way which is clean pumping.
But can you control losses?
Yeah. In this experimentally, they can also devise losses in a reasonable way. So not always. I mean, yeah.
In this way, you account just revolution of your states.
Sorry.
You are not taking into account the visibility or dynamic state. So these losses maintains the purity of states.
What do you mean? No. What do you mean that maintains the purity of the states?
Because if you start from a state and you apply this kind of dynamics without any lambda or something like this,
yes.
End up with an
Yes. We are purposely making an approximation. We are assuming we are not describing as a Lindblad. If this is equivalent to the description of a Lindblad in an oblique limit, exactly. So if you it's like, well, but since you are assuming that actually I haven't mentioned, what we will do is always in approximation in which we have only one excitation in the system, okay? Just one excitation. So you have one atom, only one which is excited, and this has a probability once of going away. So there's one excitation in your system. It means that once the excitation is gone away, the system is in the vacuum, and I'd say the game is stopped. And you start the game, you're gay. Okay, so that's equivalent to say that you are in the no-click limit. So you simply look at dynamics which last as long as your excitation is still there in your system. Okay, so in that sense, your dynamics is not trace preserving. So it's not a Limbla dynamics, and that's because you are describing your dynamics effectively with a non-Hermitian Hamiltonian. You are not describing in a full way, but still, if you are content with the fact that you are describing these transient dynamics, you can still look at it as a pure states, and everything works nicely. Okay, so it's
Yes, I'm just thinking because.
So you are giving up the recycling term in the Lindblad, essentially.
I understand what you are doing, but maybe I have still understand what I do.
Okay, yeah.
Is the US.
Yeah, of course. Now that was the photonic degrees of freedom. Now we have the emitters. We put the emitters, and again we put emitters only here, only on the lossy cavities, and we leave the other part untouched. And again, in the rotating wave approximation, you run that game that I was mentioning before, and you can extract the effective Hamiltonian using that procedure, which is the.
Quick stupid question.
Go.
What if I substitute a non-reciprocal to other systems?
It's the same thing. As long as you stay in a single excitation, you don't see the effect of. If you look at the effective Hamiltonian, then you can start looking at for example, the range of interaction between these emitters. And indeed, you see that from this picture that as you change the value of your loss of your photonic waveguide by changing, for example, gamma or changing J, you can explore different range of interactions. In particular, you see that in the limit in which gamma is negligible, you have a long range interaction, meaning that essentially every single atom interacts with every other atom, which is kind of unknown things in this context. If you switch on gamma, you see that the range becomes smaller and smaller up to the sweet spot where you have the exceptional point. In the exceptional point, it becomes exactly nearest neighbor, so it's very localized, the interaction. So this interacts only with that and doesn't interact backwards. It doesn't interact with the next nearest neighbor and so on. And on top of that, there is another peculiarity. You see that the interaction is chiral. You see that from this in the extreme situation at the exceptional point, you see that this guy here interacts only with this guy here and doesn't interact with the guy up. So it means that the interaction happens only in this direction, and this does not interact with the one behind. So it's chiral.
You have a quantum phase transition.
I don't know whether you can call it phase transition. It surely looks peculiar. Huh?
I would say it's a quantum phase transistor.
I don't know. Yeah, because yeah, it is Angie indeed.
You are going, if it is one dimensional, you are going from short range to long range interaction.
But you do it in a smooth way, right? So you actually start from everyone with everyone, and then you can tune it very smoothly. So there's no sudden change from as you change the parameter. So I wouldn't call it phase transition. But surely something weird happens here.
I didn't tell in English. Is there a quantum phase?
Okay. I don't think there is a phase transition, but I don't know. So it was a question mark.
Yes.
I didn't see the question mark.
You see, he was reading England.
So I don't know what, I mean, this looks peculiar to me. I don't know, because it's, the There's some non-linearity going on there, but I don't know whether you can call it a transition of any sort. The third interesting thing is that these plots here do not depend on the boundary condition of your lattice. In the sense that if you start from a photonic band, a photonic lattice, which is periodic, then you get this picture here, meaning that the last and the first of your lattice is actually interacting as if they were nearest neighbor, nothing weird happening there. But if you at some point break the photonic lattice and you have open boundary conditions, this picture remains the same, exactly the same. It's completely insensitive. So the last and the first interacts as if they were nearest neighbor. The last and the first atoms. Okay, so you are breaking the boundary condition of the lattice, and the first and the last atoms interact as if they were nearest neighbor, which is very weird. So I'll tell you more in a bit. So the peculiarity of this model is that it is chiral, it is next neighbor at exceptional point, and it is insensitive to the boundary condition. Then I'll tell you why this is happening for some intuitive arguments. So you have two types of chirality in your system. One is the sort of non-reciprocity, and another is the so-called bilocal coupling. I'll tell you in a bit what they are. So what is non-reciprocity? So look at this lattice. You can make a local transformation to this lattice, meaning that you make sort of a unitary transformation at the level of the lattice, and this transforms very simply in this configuration. So this lattice becomes this simple lattice like this, and then notice that the atoms doesn't interact anymore with only with P, but interacts with two sides, just because you have made a unitary transformation on this level. So somehow you made a unitary operation, and this made have to take into account this interaction that you are actually, this is split into two, right? So it's a rotation of this, essentially. Notice that this becomes much simpler to interpret in a way, because you have this transformation tells you that in this point of view, you have some non-reciprocity. What it means that photons likes to propagate more towards the left than towards the right, because this gamma term here emphasizes the propagation towards the left than towards the right. Okay, so it's that's
what I was saying. I mean, that there must be some destructive interference condition that okay.
And then
that gives one of them.
Oh, one of which?
One of the directions.
No, this is just an effect. This is just an effect of rewriting simply your Hamiltonian on a different base.
But if you just make the combination of symmetric and asymmetric, you can, in principle, sometimes you tune parameters and something goes to zero.
This here.
Yeah.
This. Yeah, of course. If you can tune such that this is completely this goes to zero at the sweet spot.
I'm blind.
So this becomes exactly zero. Yes, yeah, okay. It's completely non-reciprocal in that case. So what is? Let's analyze these two effects separately. So suppose that instead of having that complicated lattice, you have just a tight binding, very simple. Every single cavity interacts normally in this way. Everything is Hermitian and so forth. Now you have a bilocal coupling. If you have a bilocal coupling like this, you can show that if you choose the interaction between these two legs, such that they are with a specific type of phase difference, then you can destructively interfere the emission of a photon towards the left, and constructively interfere the emission of a photon towards the right. Therefore, these emitters only emits photons towards the right because of this specific choice of this coupling point. Now, you also have this non-reciprocity, meaning that photons likes to propagate leftwards. These photons wants to propagate rightwards, are emitted by the emitters rightwards, but naturally in this lattice, photons propagate leftwards. So if you mix up these two non-reciprocity, the effect is that the photon emitted is chiral because it's emitted towards the left, but the tendency of the lattice itself is to counter-react somewhat, to limit the propagation, and this because the photon would like to propagate rightwards, and therefore this combination of these two effects, which are counterbalance each other, gives rise to this to the emission of the photon, which is bound in the neighborhood of the emitter, which gives rise to an atom photon bound state. And now you see that the atom photon bound state is chiral, only in one direction. And you can see that as you change gamma, the photon losses, you can go from a situation in which the photons freely emits on the right, or if you increase, you can get to a bound state, which is gets squished up to a single only two sides in the sweet spot, in the exceptional point. Now, that explains why the effective interaction is chiral. Again, with the picture that we discussed initially, you have an atom is bound state, and an atom on the left sees the bound state, where an atom, sorry, on the right sees the bound state, where an atom on the right doesn't see anything, so it doesn't interact. Okay, so that's explained the chirality. But what about the open boundary conditions and the insensitivity to the boundary conditions? As I said before, you see, if you have an excitation here, this excitation travels only in one direction. And that's fine as long as you have a photonic lattice which is periodic. But if your photonic lattice is broken here, somewhat, the counterintuitive effect is that this excitation emitted here somewhat doesn't care and goes into this one. So it's somewhat insensitive to the fact that there is a gap here. But still, is the interaction is mediated by the photon lattice. So how comes it's insensitive to the fact that the photonic lattice has open boundary conditions? And there's an explanation, intuitive explanation for that, although it's not yet completely understood yet in some details. So you have if you look at the interaction in the bulk, so two next neighbor in the bulk, the reason why they interact is because they interact to the rest state, right, the bound state. But if you place the atom here at the very end, now this is not anymore the correct picture of the rest state, just because you are missing something on the right. So breaking the boundary condition somewhat gives rise to you have to think again how to describe your rest state. And actually, what happens is that there is one eigenstate of your photonic lattice which we didn't actually take into account so far. And there is one eigenstate which is living in the lossless cavities here, and this state is propagating freely from left to right. Now, the fact that you have cut the boundary condition here, you are able to hybridize this bound state here with this extended state here. And this extended state here, which lives in the lossless cavity again, goes all the way to your lattice up to the other side and is hybridized with a possible bound state on the other side. So the idea, eventually, what you end up is that your bound state is not anymore that little bound state that we have seen before, but it's exactly, it looks like an extended bound state, okay, which has this shape.
And this dies when cavities are not lossless.
Yes, if you, as soon as you put some lossy here, lossless.
No.
If you lose here.
No, don't make lossy the red ones.
If you don't make the red ones lossy, no. If you have, this happens every time you have, for any situation. The point is, if you have the cavities which are not lossy, then this game becomes boring because every single atoms interact with every single atoms. So you are not surprised by the fact that these interact with this one, because every single atoms interact in the same way, where you have no losses, because
No, but you have this localized state.
the surprising fact is that here states interact only next neighboring, except for these two ending points.
This is some sort of effect.
No, it's not related. No, there is some suspect that it might have some relation with some non-emission topology, but we haven't yet fully fleshed out the reason.
As far as I understand, what you have at the bottom is a fundamental model.
Yeah, if you look only on this one, yeah, it's actually just one mode. It's only one mode which is transporting this information from this excitation from left to right. So just one. You need just one mode which is able to do that. Also the nice thing is the other nice thing is that all the other atoms you place in between, since you place them on the lossy cavity, they do not see this stress state. So basically, they do not interact. So only this interact with that, and in the middle, nothing. No other atoms are actually seeing it. And the effect of this is that these two emitters, the ending emitters, interact with each other as if they were next neighboring, and the others are completely do not see any type of effects. Do not see the excitation traveling in this extra mode. Okay.
The interaction between the edges is the same as nearest neighbors.
That's the point. We haven't figured out. We have analytical reason to show in this model why this is happening. So we, apart from numerics, we have seen actually analytically you can prove it nicely. The point is that we do not have a general proof as to why the interaction is exactly the same. So the fact that they can interact, initial and last, somewhat is understood. This picture is kind of a realistic picture of what's happening. But this doesn't explain why the interaction between this and this is exactly the same interaction that will happen between these two next things. So, which is kind of, so we do not why in general and how general a model will display this type of behavior.
Haven't we seen, it might be my blindness, but we can see this lower chain as a normal chain, a lossless chain for not the state within the atoms, the emitters, but between two different emitters, which are not the emitters we are using, but a combination of the emitters and the cavity.
So again,
can we see the non-lossy cavities as since we have a chiral relation on the higher chain?
Yeah.
Can we see the lower chain as a lossless chain between two single states rather than the chain itself?
So as if the lower chain was the
middle chain doesn't exist in a sense.
What do you mean the middle chain?
The lossy cavity, since it's lossy and since we've seen the chirality of their interaction, can we see the
as this one was non-existent?
Yeah. Due to the nature of the interaction we have seen up to now.
Technically, what's happening, not technically, actually, these modes here, so there are many modes which actually there are many modes which different modes which live in the lower lossy cavities, which actually play an active role in the interactions between every atoms here in the middle. Of all the possible modes in which these atoms are involved in, there's only one mode which is conveying this information. So the situation is not like you are splitting, if I understood, you are splitting your chain as an upper chain which is lossy and a lower chain which is lossless, and then we are using only the upper chain to make interaction between the atoms and the lower chain to transfer the information from left to right. No, because it's a more complicated thing. Okay, so it's only one single mode.
So do you have some idea about the solution here in terms of the mapped model?
Sorry?
This is Eigen state here.
Mm-hmm.
In terms of the mapped model, so there's a sort of a Nathan-Nelson model.
Mm-hmm.
So
it is Nathan-Nelson. No, it's an SSH. It's similar to Nathan-Nelson. It's the non-Hermitian SSH.
Okay. So if I want to describe in terms of that model, this solution,
you can do it.
Yes, no, because
I don't know whether it's fruitful in the sense that you get a better image of that because
it would be useful to understand why the interaction here is the same in the case of short. If I change a basis, maybe I have some.
Maybe. I don't know. I think this conveys the intuitive picture because of you immediately see the lossless. Where is the lossless modes coming from?
This picture makes clear why.
Exactly. So if you have ideas, please come in because it's like a year and a half that I'm struggling to understand why.
How resilient is it to defects?
That's a good question. I don't know. Maybe it's not at all resilient. We haven't tried it. Yeah, maybe it's just as you put something, maybe it goes away easily because maybe it relies on symmetries of your system. Maybe yes, that's a good point. We should.
Sometimes
maybe there's
are approximate.
That's a good point because if this effect relies on some topology, non-Hermitian topology, maybe it should be resilient. Maybe there is inherit some topological feature, and then defects is not going to play a role. I don't know. Haven't tried.
Good question. Does the Hamiltonian strength depend on the size of the system?
Sorry? No.
It's very insensitive.
Totally insensitive. So that's again kind of a very. Also, we prove it in the thermodynamic limit. So you can analytically prove these things in the thermodynamic limit. So you take this, and it's infinitely long. The point is, of course, all this game is played on the assumption that you have an effective description, which means that you are in a Markovian limit. So you do not see photons propagating if you are in this approximation. So everything happens instantaneously in this approximation. What really happens is that the photon is emitted and it takes some time to travel all the way here. And then actually we've seen in some simulations that you see the photons traveling, but the time is so quick compared to the time scales of your system that is effectively instantaneous. So,
but this independence of the boundary condition depends on the presence of non-lossy cavities. Because if I have both lossy cavities,
yes, it's strictly dependent on the fact that you have one mode which is lossless. You have to one thing that I'm sure is that you have to have one mode which is at least one mode which is lossless in your.
I know that in non-Hermitian and Hamiltonian there is a skin effect, so typically the properties depend on the boundary condition. Is this a particular non-Hermitian?
This is kind of this is the converse, I would say, because there you have, but probably there is some indication. my intuition that there is connection with the skin effect, but I haven't yet managed to. One day I think the one way, and the other I think the opposite. So I haven't. Okay, so this was the first part. I'm sorry I'm taking so long. I don't know whether I have time to the second part. Shall I?
Who has to go? Because no one wants.
It took longer than. Oh, it's good. It's good. Yeah, I'm happy that. No, I'm saying that I don't want to impose an extra time to anyone. So it's.
No, you don't impose. Nobody imposes.
Exactly. Nobody imposes anything. So feel free to go away.
He's like until midnight.
So I have to stay until midnight. Okay, I have to call home. Okay. Okay. So the main topic here is now topology. So bear a little bit with me with topology, but probably you know most. You may know more than me. So historical introduction. So the first topological interesting thing is the integer quantum Hall effect. You have this 2D electronic gas, magnetic field. You have these edge modes which carry current and charge current, and you have this transverse conductivity, which is proportional to an integer, which is the Chern number, and which is very known thing since a lot of time. And then you can also apply the same ideas without the magnetic field, with an intrinsic interaction between in your system. You have the so-called anomalous quantum Hall effect, which was known as Haldane model, quite famously. You can also show that you can have interesting effect. Later on was found out that after 2005 on, you can have a similar effect when you have two copies of the Haldane model, one with spin going up and the other with spin going down. And you can show that you can have two currents, one of spin up and the other with spin down going in the opposite direction. The net effect is you have a spin, a current, which are carrying spin and not charge. So these are called, in fact, quantum spin Hall effect. And you can show that you can go beyond 2D, you can have a 3D so-called topological oscillator, which instead of having edge current, you have surface current. So, but the physics is very similar. All these effects are being predated by the SSH model, which was actually the first topological model, which is a 1D model, and you have again the appearance of, instead of 1D and 2D edge modes, you have zero-dimensional edge states at the two ends, depending on some topological interesting situation that you can have. These are borne out in a condensed matter field, but you can also translate these type of things also in photonics. So using photonic degrees of freedom, so you can replace electrons with photons essentially, and you can have similar effects, which have nowadays becoming a field by itself, which is called topological photonics. Now, the idea is, shall we put emitters in this type of environment and see what happens? And then by merging these two ideas, it's what you may call topological quantum optics, if you want. So it's which is the best of the two, I would say. As I already kind of anticipated, you can have interesting effects if you have this environment with interesting topological physics when you put atoms in this type of environment. Now, the questions of the second part, it's kind of simple. I already introduced what's an effective Hamiltonian of atoms which are interacting with a given waveguide. Now, the question I would like to ask is, if you have a waveguide with a given non-trivial topological situation in the sense that I described before. So it's some topological number here. Is the effective Hamiltonian of the atom interacting with this environment kind of inheriting the same topology, a different topology? Can I say anything about the topology of the effective Hamiltonian? Okay, so we know the topology of this. Can we say about the topology of that? That's the question. Okay, and the answer is kind of no, I'm not giving you the answer yet. So again, the situation is similar as before. Approximation is the same, with the extra assumption that the emitters are arranged in a periodic arrangement. So, because otherwise it's difficult to discuss about the topology of the lattices. If you have this periodic arrangement, you can go in the Bloch description in terms of quasi-momenta, and the effective Bloch Hamiltonian is related to the Bloch Hamiltonian of your lattice by this simple mapping. Okay, Bloch goes into Bloch. But let me just be a little bit more formal. What it means to have topology, what it means topology. Topology, for a theoretical point of view, it's a way of distinguish families of Hamiltonians. So we say that two Hamiltonians are topologically equivalent if I can go from one Hamiltonian to the other in a adiabatic way, so by changing your parameter of your system without closing a possible gap that you have in your system. So that's the standard definition, right? So pretty much as you go from a cup to a donut without closing the whole of your donut. Okay, so pretty much in the same. It's an analogy, which is I have to do that. We talk about topology. You have to give that picture. So so similarly, you can discuss about non-emission topology in a similar way. Now, you have non-emission stuff, so we have a spectrum which is not anymore real, but you have a complex spectrum. So these are representation of a complex spectrum, and when you have a complex spectrum, you can have very peculiar shape. Someone mentioned already skin effect. So when you have a skin effect, or whatever it is, you can have this loop forming in your spectrum. And you can call to a Hamiltonian topologically equivalent, or inequivalent in this case, if you, by fixing a reference energy, you cannot go from one Hamiltonian to the other without crossing with your spectrum, crossing this reference point. Okay? So if you have a loop, it's a typical situation in which you have a topologically non-trivial situation, topological non-trivial Hamiltonian. Going back to the ideas that we were discussing just before, you can describe the topology of this emission situation using some topological invariant, which is in this case is the well-known Chern number. But you can, and it's very important, it's well known that in order to have the quantum Hall effect, the integer quantum Hall effect, you have to break time reversal symmetries, in this case by using the magnetic field. But that's not the whole story, because you can have interesting topological physics also without breaking the time reversal symmetry. And that's the case of the spin Hall effect, in which you have also a topological invariant. In this case, in the Chern number is a topological invariant, which is an integer. Whereas in the case of the spin Hall effect, the topological invariant is an integer modulus 2. So it can only be 0 or 1. So you have only two possible topological configurations. Similarly, you can also have time reversal preserved in this type of situation, which guarantees that you can have topologically non-trivial situation with zeta 2 invariant. Now you already also in the SSH model, you have topological invariant, which is called the winding number, and that's guaranteed by the existence of a symmetry, which is called the sublattice symmetry, or chiral symmetry. So this brings already you may have realized that symmetry is very important, and dimensionality is also very important in order to have topological effects. And indeed, you can describe fully the possible plethora of topological behavior by this periodic table, which is called the Atlan-Zimbauer classes periodic table. You only have 10 different classes that you have of topological materials, and these are described by the type of symmetry, which are time-result symmetries, particle Hall symmetries, chiral symmetries, depending on the fact that you have these symmetries and the dimensionality of your system, which could be 1, 2, 3, or whatever. Then you have, whether you have a 0, you have a topological trivial material. If you have a number here, which can either be Z or Z2, you have a possible interesting object, topologically speaking. So as you notice from this picture, you had either Z or Z2. There are other possibilities of topological quantum numbers. Okay, so that was just an introduction to this type of things. Of course, you can go into a non-emission domain, and when you have non-emission domain, because of the fact that complex conjugation doesn't coincide with transposition, you have a proliferation of symmetries that you have, and then you go from 10 symmetry classes to 38 symmetry classes. You have many more possible type of topological objects, which are called the Berner-Leclerc topological classes. But don't worry, we are not going into that. So the result of this that I want to mention is the following. Suppose that you know the topology of your underlying lattice. There are only two possibilities, as we said, either Z2 or Z type of topology. You can show that if you tune your atoms, in resonantly to your lattices, resonantly, then there is only two possibilities that can happen. First of all, if you do that, the classes, topological classes of your effective Hamiltonian of the atoms is exactly the same as the topological classes of the underlying lattice. First, if your underlying lattice has topologically as a topological number of type Z2, then this one has the same topological number and inherits the same topology. So if this is as interesting, let's say, some edge states, also this one has interesting edge states. Okay. The case becomes slightly more complicated if you look at topological lattices which have Z type of invariant. So chair number, winding number. Stuff like that. You can have only two the underlying lattice. Now I'll give you some example. Otherwise, what happened? Oh, l'ha buttato fuori.
Sempre prima di essere bloccato.
Forse finito il tempo.
Abbiamo.
Sì.
Sì. Sì, Ciresi sei andata perché aveva.
Abbiamo fatto il controllo senza mossa.
Funziona, no?
Non sto registrando. Ah, non riuscito a registrare.
Dove funzionare?
Ma forse funziona.
Sì.
Ok. Abbi.
Ci ha buttato poi?
No, nessuno funziona. Angelella per registrare.
Ah.
Okay. So, and the fact that you have the same topology of opposite topology depends only on dimensionality and on the fact that you have emission or non-emission physics, emission or emission topology. So that's the whole story. So I can stop here if you want, but I'll give you some example. So the easiest example is the SSH model. The SSH model is a succession of cavities with interaction is alternating, and depending on the fact that these two interactions, as you tune this interaction, you can have a trivial or non-trivial topology, in the sense that you can define a winding number, which is your topological number, and so on. But physically, what happens if you open the boundary condition of this model, and you look at the edge, you look at your spectrum, you see that there are two excitations in the middle of the gap of your spectrum, and these excitations corresponds to two localized edge states on the two ends of your chain. So, and that happens only if your topological number of this SSH model is non-trivial. So it's different from zero. Okay. So now let's place atoms. If you place atoms, we can ask ourselves, what's the topology of this Hamiltonian, the effective Hamiltonian? This could be very complicated because in general is a long-range Hamiltonian. Now, what it means to check whether these are topologically non-trivial? Let's have a look. By the scheme that I was saying before, we expect the same topology. So let's see what happens. What we do, we open the boundary condition of this, only of this, not the underlying lattice, only of this. And what happens is, as anticipated somewhat, we have a non-trivial topology because we see at the level of the atoms, there is edge states at the two ends of the degrees of freedom of the atoms. So the degrees of freedom of the atoms, so the effective Hamiltonian, is non-trivial in the same way in which is non-trivial the Hamiltonian of the underlying lattice. Okay, so inherits the same topology.
Removing two atoms.
Just to make open boundary conditions.
But say that the fully connected atomic lattice is still fully connected.
It's not fully connected because you're missing some. Yeah, it's the same Hamiltonian. The same Hamiltonian.
I mean, it is almost the same.
Except from
except that you removed.
Yes. But I'm saying that it's not fully connected. It's very long range, but it's not extremely long range, as in the case that was mentioned.
No, let's say if I just take forget about the cavities, take the atoms and put it near. I mean, I see all the, probably I do not see, but I see that there are still all the connection between the remaining ones.
Yes, yeah, because you are simply taking out the others. These two, yeah. But the point is that independently of how complicated this Hamiltonian is going to be, it's very hard to see if you look at the Hamiltonian whether it is trivial or not. And no matter how complicated it is actually you can tell the fact that this is non-trivial, but because it comes from an effective Hamiltonian that has inherited the topology of the underlying lattice.
It makes sense to only remove one atom from the.
Just complicated the description. If you remove one atom, this is not what usually is the core. Is the.
Yeah, I mean, it kind of loses the meaning of having self-connected.
What do you mean? You remove
just
one
only
atom.
one atom.
You have to remove the cell to be
so
entirely.
Do atoms form kind of cells?
Yes. Two atoms, forms a cell. Yes. See, it's the same structure. It's the same minimal structure as the underlying lattice. So you have two cells here. You have two cells here.
E and W being equal to each other at the atomic level.
At the atomic level, no.
At the atomic level, there is no difference in between inter and intra cell.
There's no. It's very much more mixed up. The idea what's intra, what's extra, because. But still, there is the meaning of being cell. What is the cell? Okay. So another interesting things happens when you, for example, take a 2D system, and this the case of the QWZ model, which is totally equivalent to the Haldane model. So it's topological, and forget about the lollipops here at the moment. For the moment, and look at this gray area here. This gray area is your photonic lattice. This photonic lattice is topological. You can simply diagonalize it, and you see there is that bulk modes, which are this gray area here, which is hardly C probably, and you also have these. If you quantize on a cylinder, this is quantized on a cylinder, periodic in this direction, but is cut in this direction. You see that there is formation of these edge modes in these two sides. Red stands for left and for right, and blue for left, which should be the other way around. And you see that the slope of these modes, they are only propagating in one direction. So the red one is propagating in this direction by the slope, and the blue one is propagating in the opposite direction because of the slope. Okay, so that's the edge states, the standard edge states. So now you can look at the spectrum of the lollipop. It's actually here, the spectrum of the lollipop. You don't see it because it's a very fine line, because it's actually the diagonalization of the whole thing. So, but if you zoom in, you see that also this lollipop here, the atoms, these are the atoms. At the level of the atoms, you have a band structure here, and you also have edge states. And as you can see, the red one is going down here, whereas here is going up. So it's actually the other way around. So the edge states at the level of the atoms, have a chirality which is completely opposite. So this is due to the fact that you have a Chern number with opposite value, exactly the opposite value, and that's because we are in 2D. So according to this scheme, we expected this to be the same, this to have opposite. So
there is a sort of effect globally, because the total Hamiltonian behavior
kind of. Now there's one important thing that you can also show, that if you see that there is a little bit of space here. If you make this space between the edge of the photon lattice and the edge of the atom lattice go smaller and smaller, these two kind of overlap, they hybridize, and the Chern number goes away. So you have to have these sufficiently far away so that the atomic degrees of freedom sees the underlying lattice as a continuum and doesn't see the end of the edge. Okay. So that's which is pretty much in the same spirit.
To the electron gas in all effect.
Exactly. So it's a kind of remind, but yes, it is. I don't. Yeah, but the reason is different. There you engineer that effect. Here it comes naturally because of the effective Hamiltonian. You can repeat the same argument with an emission, non-emission stuff. These are the Gattaro-Nelson model you mentioned before, that you have no reciprocity, and then it's characterized by the fact that you have this loop, as you mentioned before, and this loop winds in one direction. As you open up the boundary condition of this model, the spectrum changes dramatically, which is the skin effect, and the effect is that all the eigenstates are completely squashed towards one end. Every single eigenstate of your model is all squashed towards one end, okay, towards the right. And whether it is squashed to the right or to the left is due to the value of the winding number. If the winding number is clockwise, you get this effect. If it's counterclockwise, it's squashed the other way around. Okay, so then you place your atoms, you look at effective Hamiltonian, and you ask what is going to happen at the level, at the spectrum of the effective Hamiltonian. You see the formation of another loop. But the loop is revolving, is winding in the opposite direction, as we expected from this scheme. The winding number gets an opposite sign, and that's what is the and when you open the boundary condition of the level of the atom, you have this skin effect, but on the other side. Okay. Again, this compatible with an interesting things that you can show. It's a publication, which is a very nice recent publication, which shows that you can always make a sort of mapping between a d-dimensional model, non-Hermitian model, to a d+1 Hermitian model. And the topology of this is kind of related to the topology of that. And if you consider this mapping, you see that this topological reversal is perfectly compatible with this mapping here. So it's completely consistent with this mapping that is known. You can play also in 2D, but don't worry, let's keep it. So if you want, I can give you a full proof, a sketch of the proof and why this is happening. Don't know. It's up to you. It's a kind of one slide. It's just one slide and we finish. Let's sketch it. Okay, so as I mentioned to you before, under the assumption that I mentioned to you before, the class of the Hamiltonian, the effective Hamiltonian has this shape. If you go in resonance, the effective Hamiltonian, the block Hamiltonian, is exactly minus g squared times the photonic Hamiltonian to the -1. It's very simple. This is a mapping, as you can see, and we also know, I mentioned before, that these two Hamiltonian maintain the same symmetries. If you have chiral symmetries, the other kind of symmetries, time symmetries, and so forth. So it means that they belong to the same class. Now, this means that this is a mapping from one class to itself. Okay, mathematically speaking, it's a map to a class to itself. The class is a group. Okay, so bear with me. The class is a group. So this is a map of a group to itself. Now, Z2 is a very boring group. Z2 is a group which is either 0, 1. And if you make an automorphism from 0 to 1, the only possible automorphism is a trivial one. So 0 is mapped to 0, 1 is mapped to 1. There's no other options. So it means that if this is topologically non-trivial, this must be topologically non-trivial and vice versa. Okay? Because there's the only possible mapping that you have within this group is the non-trivial one. Things get slightly more complicated if your topological invariant is of type Z. When you have the group Z allows for two different type of automorphism. One, which is the trivial automorphism, so 0 goes to 0, but 1 goes to 1, and blah, blah, blah. Or the opposite, 0 goes to 0, but 1 goes to -1. So the only two possible automorphisms within the group of Z. And that tells you that you have only two possible situations. Then you use one trick that people in topological math use a lot, which is called band flattening. So essentially you take your Hamiltonian, you get rid of, you assume that all the eigenvalues are either 1 or -1. And you preserve only the shape of your eigenstates. This is called band flattening, this operation. This band flattening preserves the topology of your system, because the topology of the system depends only on the shape of the eigenstates, of the eigenstates, sorry. And then you see that this mapping, if you make band flattening, becomes a simple change of sign to make band flattening. So now the game becomes the following. If you have odd topological number, an odd topological number can be always expressed in this way, where Q is this is your Hamiltonian. This is the Hamiltonian for the odd topological number must be written in this way. And the topological number has this shape. You see, D is odd. You change the sign of this, you change the sign of Q, and if D is odd, this number under change of Q doesn't make any difference, right? Doesn't change. Now, if D is even, D is the dimensionality of your system. If D is even, the topological number can always be written in this complicated way. It's not too complicated, but it's this way. And you see that under change of sign, this change sign. That's it. So so that's the scale. So that's in simple terms what the mathematical reason why this is happening. You can repeat the same argument for non-emission topology. It goes similarly, but so there's not much into it that cannot be understood by this. And that's the take-home message essentially. So emission or emission, the whole story is written there. And that's the people that have been involved in this project, and that's the whole story in the two take-home messages. Thanks.